Have you ever noticed on top of your coffee or hot chocolate or tea any shapes? I'm going to turn a light on and I'm simulating what happens when the sun shines strongly through your kitchen window in the morning, or a spotlight in the kitchen catches the cup. Can you, well, first of all, you see the shadow of the rim. There's a very obvious shadow that's moving around as I move my phone torch around. But there's something else, Brady. What can you see?
It's like from where I am, it looks a bit like the letter B.
Oh yeah, B for Brady. I just thought I'd personalise your mug.
You think that looks like a bottom, don't you?
I'm going to say maybe a heart shape for sort of like repeatability, but definitely there's a bum crack there. The thing is, it's changing shape, and this shape is really ubiquitous. If there's a light coming in sideways and basically bouncing off the circular wall of a mug, anything else circular, these shapes you're seeing are called caustics. I'd like to talk about the maths of these shapes. So before we do any maths, let's talk about basically the physics here. We've got light coming in. If it goes straight in, you light up the mug and you just see a lit up bottom of the mug. You see some other things because that wall is reflective and light's bouncing around a bit, but it's not obvious what you're seeing and you don't usually notice anything. But if it comes in sideways, most of the mug is still in shadow and the only light that's getting in there is bouncing off the wall, and that wall is circular. And that's what's causing this. So we're going to do a few thought experiments. Without doing the maths, we can simulate this and see what shapes we get. And I think the simulation is quite pleasing at first. I would also like to then think about how we could even get any maths involved in what we're seeing. Spoiler is we can, but it might take some effort. Here's my crude model of a mug, and I'm going to put a light source over there. And I'm going to simulate the light source by showing some rays shining from that. Now, two observations. Where the light source is changes the direction of the rays. I hope this is not a surprise to you. We are going to have to account for that. And actually, if you saw in the demo earlier, the shapes moving as I move my light source, that's what was happening. So first thing to try is to realize that if you're getting the light from the sun is far away, Brady. Scientific Channel is aware of these facts. Very far away, so far away that the light coming in is essentially coming in parallel lines. We can model that by putting that dot way off the screen, so that's modeling our sun. And I'm going to ignore the fact that it's not going to bounce off this first thing because it's kind of coming over there and then hitting this side. So
because there's a slight angle.
Exactly, yeah. You've got to get the light in there, but it's kind of just fiddling it around until it works if you're trying to get a torch to replace this sun. So I want to show the bounce, and I've done this in GeoGebra just literally by reflecting it off the wall. Actually, I've drawn the tangent and reflected this line off the tangent, and you get this shape. You can kind of start to see maybe a suggestion of what we saw, but it's not obvious. And what's annoying about a simulation like this is if you crank up the number of rays, you just get light. So what I found really pleasing is that you can exploit the property of a piece of software and make these lines mostly transparent, but then when they do overlap, they tend to stack up. And that is exactly what is happening in real life, is that light is coming in, it's not in lines, it's just a wall of light, right? But it's traveling in straight lines. But where light tends to get more than one version of a line, we'll see it brighter.
Well, it's accumulating.
Yeah, exactly. And actually, this effect is completely familiar to all of us. They're called caustics originally because caustic comes from the word for burning. And you know what happens with ants in a magnifying glass? Not that I'm recommending behavior like that. What you're doing is focusing the light. The same thing is happening here. We're not necessarily focusing it, but we're changing the way the light overlaps, and the places where it does overlap will be brighter. So I'm going to make these transparent on the visualization, and I'm hoping we'll get a better simulation. So first of all, they've kind of gone. I don't know if the camera's picking up, but they are there. Yeah. And when we stack them up, we start to see the curve emerge.
Oh.
I really like that. But it's really nice when a simulation looks as realistic as, like, this is almost exactly what we've seen in the mug.
So you've got loads and loads of lines. Or have you got the wall, or how many lines?
I've got that's 176. You can just about see them in there still. But if I crank it up to 1,000, it's just a wall of light. And this is actually much more realistic. Light isn't in lines. It moves in straight lines. So we model it often with little lines. But being able to crank up the simulation and the overlap, like it's even capturing this fuzzy sort of splodge, which you see when you try it. There's a cusp. There's a mathematical word for a shape like this with this point. There's a cusp. And what I'd like to do is get to the bottom of what curve that is. The bum curve. The heart-shaped curve. Possibly other body part, and we'll talk about what other body part might be going on here. We have a problem, Brady, that this curve is not actually there. When I crank up the number of lines, it certainly looks like it's there, and that's the same as we're seeing in the cup. But if you can see it with making fewer lines, this curve does not exist only other than it's where a lot of the straight lines overlap. It's sort of an artifact of the fact that all the straight lines are doing what they're doing, and they happen to overlap, or rather, I'm going to use a technical word here, they are tangent to the shape we're seeing. And so here's our first clue of how to mathematically explore this. We need to find some way of thinking about that curve in terms of its tangents, because that's how we're seeing it. We're seeing lots of straight lines, no curves, but those straight lines are tangent to a curve. So I think this is why this is an appealing problem to me. Is like my instinct is like, I don't know how to get a handle on this curve. It's not even really there. But what I could do is try and get a handle on the straight lines. But it also reminds me of another famous piece of mathematical art. Here is a circle, Brady, and I've numbered some points around the circle. We could pick any rule here, but I'm going to pick the rule which is, if you take a number like the number 1, you're going to join that number to a number which is 3 times bigger than that, otherwise known as 3. But if you pick the number 5, you would join it to
15.
Amazing. And we'll do that for all of them. I'm glad you're keeping up. Let me show you what happens. So if I join 1 to 3, 2 to 6, 3 to 9, and go all the way around, we get a mess. There's a hint about something familiar about this mess that you might be guessing why I'm doing it. When you do this by hand, it's quite a fun exercise with string or with a ruler, but it gets hard to do enough numbers to really see it, which is why simulations are good. So I'm going to crank up the number of dots, and maybe you can guess what happens. And I'll show all the connections here.
Oh, hello, old friend.
The rule is you join a number to 3 times itself with straight lines. And we're seeing something familiar. The question is, does it just look the same? Or is it the same curve as we're seeing? And this is well studied. This might be called curve stitching. I feel like, Brady, I've got another video in me about this another day. But you can make these curve shapes from the straight lines, and that is a familiar context. So the thing is, you could change the rule. So just as a little glimpse of where else we could do, we didn't have to join it to 3 times. We could do 4 times. Let me show you 2. That's what happens if you join each one to double, and 3 and 4. In fact, I mean, I can just press go on this, and there's the other video. Another day. This curve stitching is like a parallel experience of what we're seeing. We could talk about the maths of this, but I'm going to dodge it for another time. I want to show you, though, that if we can think about the lines, we'd be kind of answering both situations. So we're going to think about the tangent lines to this curve. And incidentally, the curves I've just shown you, this one here, is called a nephroid. And I mentioned another body part earlier. This is coming from the word for kidney. I don't think it really looks like a kidney bean, but maybe a kidney bean, one side of it could look like that.
It looks like a couple of kidneys.
It's called a nephroid because kidney shaped, I think, is where the etymology of that word comes from. This shape is called a cardioid, and that's coming from the word for heart and shape. And it's not very heart-shaped, and it's upside down. It doesn't have a point at that end. But it's also not obvious to me which curve we're actually seeing in there, and there's a reason for that.
The bum curve.
Well, both of them have the bum crack going on here. This one has 2 cusps, and this has 1 cusp. Actually, all of these are technically called epicycloids. Again, there's another video about how they made rolling circles around other circles. But I can tell you some facts about some epicycloids, and then we're going to try and figure out if this is indeed one of them. So here's what a nephroid looks like. Nephroid is to do with a circle, and you kind of saw that in the curve stitching example. I'm going to tell you the equation of this nephroid, and I'm going to have to give it to you parametrically, which maybe scares some people, but what that means is I'm going to tell you how the x and y coordinates behave joined by a parameter. The curve is described like this: 3 cosine t plus cosine 3t. It has a sort of pleasing symmetry here, and the y coordinate is 3 sine t plus sine 3t. You should hasten to add that this describes a nephroid that's that way up. In the diagrams we were doing the other way, it's like rotated 90 degrees. There's a very similar one for the 90-degree version. Let's not worry about the difference. They're the same thing, just spun around. So to explain the parameter, this t is kind of irrelevant. It's just a number which changes, and as it changes, the x-coordinate would change and the y-coordinate change at the same time. And if you plot them together, it would trace out this curve. I should tell you the values of t that you need to use. And because it's trigonometry, maybe it's not too much of a surprise that you go between 0 and 2 pi, otherwise known as a full circle, if this was an angle, which it kind of is, but isn't necessarily an angle visually yet. If you let t travel between these two, you will get this full shape. And this creates the nephroid that goes through the point of 4. This circle has radius 4. We could have scaled it back to be radius 1. I'd have to divide everything by 4. It's just easier to work like that. So I'm going to kind of take that as given. We could do more exploration of where that has come from, but I want to start with that for now, because I want to talk about how we'd find what the equations of the tangents to this curve are, which would be the lines that do that, just touch. And there's lots of them. Every point has a tangent. And since we're working in our reflection thing with the idea of straight lines, these are the lines I need to understand. So I'm going to do some maths. And this is non-trivial maths, Brady. We're going to do some serious trigonometry. We're going to need to know our trigonometric identities. And it's possible we should give people the option to skip to the conclusion. But we're going to do it anyway. we have got the equation of a straight line which is tangent to a nephroid at any point, and that point is defined by the value t in the parameter. Glad you all watched me derive that. If you did it yourself, well done. If you didn't watch it or did it yourself, what are you doing? But the headline is this, so I'm going to write that down on our other piece of paper. Don't need that anymore.
Get rid of it, don't need that.
Let me get this right. The tangent equation is y sine 2t plus x cos 2t equals 4 cos t. And it is worth checking what that means.
So you're saying that? So you're saying any tangent of this shape here, I put in,
would satisfy this.
right? Yeah.
For some value of t. On the screen you can see these are the equations we started with, and it's tracing out that nephroid for a given value of t. If I just type that in, it should give us a straight line that moves around on the edge of it. Let's trust the maths. Y sine 2t plus x times cosine of 2t equals 4 cosine of t. It's like magic. That's really pleasing to me. It's a straight line, but wherever it is on the curve, it is the tangent to it. And this is good because we think this sort of straight line is the thing that's causing this to appear in the mug. Light's moving in straight lines. If it overlaps in certain ways, it's going to make this shape and there'd have to be tangents. So our next job is to check whether does light coming in at straight lines bounce at angles which satisfy this. If we can prove that, we're done. Okay, so part 2 is think about the physics and the reflections. I'm going to draw a bit of our mug. Here's a sort of quarter of our mug, like top right quarter here. And the center of that circle is here. I'm going to imagine the light coming in straight lines up here. So let's draw the light coming in. And remember, I'm also assuming that my light source is really far away enough that all the lines come in parallel. It would be different if they were coming from somewhere closer. It would bounce off the wall in that sort of direction. And what I want to do is find out the equation of this bounce, because it's the bounce that's causing the effect we're seeing. So I want to get the equation of that straight line from the fact that this is a circle. And that's not obvious, but there's more trigonometry to do. This bit is worth seeing though. So this point here, I'm going to draw a line from the center of the circle. And I hope you remember from some other videos we've done, Brady, that a point on a circle is defined by trigonometry. If you're at an angle of theta from this positive horizontal, this point is in fact cos theta sine theta. That's the definition of a circle. And for people who don't know it, it feels like, why is trigonometry to do with circles? It's all to do with circles. However, our circle is radius 4, so we do need to scale this up by 4. And now I need to do some angle chasing, which they call it in the trade. I'm going to draw this theta angle and see what's going on. We know about reflections. The angle of incidence is the same as the angle of reflection. I hope this is a familiar thing. So that angle there is not theta. This is a right angle, but it is the same as that one. So we might use that in a minute. What I really want is this straight line dotted going down here, which is the line I want to find the equation of. I want to find its gradient, and then I've got a similar technique to last time. Once I've got its gradient and the point, I can get the equation of the straight line. So I need to know this angle here, and I think we can get it. I'm going to draw the tangent to the circle in here, which is right angle to the radius, and I think I'm going to claim that if that's theta, that's 90 minus theta, or pi by 2 minus theta if we're working in radians, which means this is again theta, and this is the reflection ray carried on that way. So again, it's going to be theta because it has to be the same both these. And then all the way up to the top is 90 degrees, so, or pi by 2. I've gone quite quick, but check if you don't believe me. That angle in there is the whole 90 degrees, otherwise known as pi by 2. Take away 2 theta. That's important because I now know that with any angle of a line, the gradient of that line is the tangent of that. Now this is a negative angle, it's coming down. So the gradient of this line, and this is our headline, is tan of negative pi by 2 plus 2 theta. Now the gory detail kicks in, which I'm going to get another bit of paper for.
That wasn't gory.
That was slightly gory, but it's diagrammatically gory, which I feel slightly happier about. Algebraically, trigonometrically gory is another level of gore.
And what are we going to do on this other bit of paper for people who go and watch?
What I'm going to do is try and derive the equation of that reflection line. And if it's the same equation that we got for the others, we have some evidence to say that the curve we're seeing is a nephroid.
All right, we're back in the real video.
So I've done some gory detail. I'm glad you watched. Or did it yourself, because of course you did one of those two things. Let me write the summary, and then we'll get rid of this bit of paper, which is, in fact, we'll get rid of it. This one concluded that the equation of this ray is y sine 2 theta plus x cosine 2 theta equals 4 cosine theta. Now that
And that looks just like that,
It's
except
very like that. What do you notice the difference?
that one's got T's in it and that one's got the thetas.
So this is where our notation needs to be quickly explained. The t was a parameter that helped us draw this curve. You pick a t, you're somewhere on the curve. This was an entirely different thing. This theta is the theta that controls where you've hit the circle. Different theta, you've hit the circle at a different point. So they're both parameters, but they're different ones. This is a parameter controlling which light ray you're analysing, and the t was a parameter for where on the curve are you. And that's really helpful because this theta parameter has some limits on it. Because I'm hitting the back of the mug, right? One side of it, I can't hit all the way around the circle. So I should limit theta to between 0, which is kind of over here, and pi over there. So I should probably add theta is between there, which means I won't get the whole nephroid, I only get half of it, which I hope is beginning to be a relief, because when you looked in the cup, you didn't see the full kidney shape or whatever shape that both sides of it, you only saw one of them, and that's backing us up. The parameter is only like for half of it. But what it's telling us is that the reflected light rays are all of the format, which is exactly the same as tangents to a nephroid. It's enough for me. The shape we're seeing is a nephroid if the light is coming from so far away that it's all coming in parallel. Now,
You know what I just noticed? Like we also called it a heart shape.
yeah.
And look at the mug we used. It's got a heart around.
Oh, there's a heart on the teacup.
There was already a heart on there.
Well, the thing is, inside it, we've just proved it's not a heart, it's a kidney, whatever naming. However, we could do this entire process again. I can see your face. we could do it again. Instead of assuming the rays are like infinitely far away, we could put them on the edge of the cup, and then they're becoming at angles. And actually, if we did the same process, we get equations of tangents to a cardioid. And that is named after the heart shape, even if it doesn't look like a heart. So the reason I wanted to go through this is, first of all, there's a shape in here which you will see every time you look at anything reflecting off a circle. It becomes really easy to spot it once you've noticed it. And if you look it up on the internet, a lot of people say, oh, it's a nephroid. And then the next website says it's a cardioid. And they're both right. It depends on where the light's coming from. What I wanted to do was demonstrate the sort of maths behind figuring it out. I do not think it's obvious how to come up with a curve, which is never actually there. It's an illusion. So the idea of looking at tangents is a nice idea. The actual maths, like the grunt work of doing the trig, is a pain. It's like, as a sportsman, it's the sort of sprint training you do so that you can do a sprint when you need to. No mathematician really likes turning the handle and solving the things. It's satisfying. It's also frustrating, which is why it's definitely an optional part of the story.
And we're seeing it because that's where the light is sort of stacking up. Most of the light rays are going onto those
What
points.
we've proved is that light rays, when they bounce, will always be tangential to a curve, which happens to be a nephroid, and so that's where they will overlap, because they'll always be on that boundary. But there's some other nice questions to finish with, is what happens if it bounces again? So here's what we had before. We've got the lovely nephroid appearing, but let's just check the other conclusion, which we didn't prove, but hey, knock yourself out if you want to do it. If you put the light source closer, you can see the shape changing, right? You can see out there nephroidy, or at least half nephroid. You're going close, you can see the curve almost kind of completing itself. It's going all the way around here now. This is actually what they call a cardioid. And if I put it right on the circle, that's a different shape. It looks similar enough that I don't think you'd noticed it in the mug. However, what happens if the light, once it's gone in, it bounces once and we see it on the bottom? It's conceivable that it could bounce again. It's always going to be fainter because things lose brightness. But
So it bounces off the cup a second time.
yeah, well, I want to know what happens. And since we've got a simulation, we can do it. Let's put the second bounce on. And here is what the second bounce looks like. I coloured it in a vaguely red colour because it's more heart shape, if you ask me. And actually, this is another epicycloid you can get from curve stitching. I'm not going to go into the mathematics of it, but the simulation says we should be able to see that shape if we can get the lights to let us see the second bounce.
So like if the cup was like a mirror or something inside.
Yeah, and there were no other light sources to confuse things, and you angle it right. And there's all sorts of practical things like physics is, but the mathematics is the pure thing. It should do that. It's just that you don't often see that, I think, because the first bounce trumps it, like sort of washes everything else out. Now we can go further, right? We could do a third bounce, did it in green, but hey, that's the most heart-shaped of the lot. So there is a heart in your teacup and not just on the outside. Very nice, Brady. I would like to try seeing the second one as a bit of an experiment because I have a very reflective circular item. And many people do. Here's a wedding ring. It's my wedding ring, in fact. My wife didn't leave me after the last video.
When you got her number wrong on her.
Don't remind them.
Yeah.
But this is reflective inside. I think we should try and turn the lights out and see what we can recreate.
Let's do it. Lights out.
Right, so we're in the dark, Brady. That you can see some reflections in there, but it's probably very hard to pick up. I'm going to turn my phone torch on. As soon as I do it, can you see it? And then we can see the second bounce if I make the first bounce less.
There we go, yeah. There's the second bounce.
Sit back and relax with a cup of tea or coffee and check out the latest offerings from Brilliant. This is a first-rate collection of courses and content that will, like rays of light bouncing around a mug, blow your mind. They're all over the world of math, science, computer programming. This stuff's going to have you thinking like a scientist or thinking like a mathematician. And who knows what opportunities can come from that. Maybe a change in career path. Or just being that little bit smarter, better grasping those little things you see around you every day, but don't quite understand. Everything on Brilliant's elegantly designed, highly interactive, and made by people who are passionate about learning. To try Brilliant for free, visit brilliant.org/numberphile or scan the QR code there on screen. There's also a link in the description. You'll get 20% off an annual premium subscription. Also in the description you'll find some more links, the extra working out that we cut to over on Numberphile too if you want to go and see that in more detail. And patrons can go and see more of the fancy bouncing light and stuff like this that our animator Pete did when he was helping make the video. Plus over on Ben's own YouTube channel you can have a look at a really long in-depth video at how all the GeoGebra stuff works, how Ben does these animations. It's always really interesting, fascinating seeing how it all works. So go have a look at that too. Links below.